Hello, my name is Chris Gamache, and I'm happy to join you here today to talk about anchoring in seismic events. And I am with Hilti. I am a manager of anchor approvals and technical data for Hilti in North America with our anchoring products. I've been with Hilti almost 20 years, mostly in the testing and evaluation of our products with some research. And before that, I was a structural engineer as a licensed structural engineer from the state of Colorado in the United States, and currently residing in our Dallas office with the Hilti organization. The anchor, well, whether a cast-in-place anchor or a post-installed anchor, is a very key part to the structural load path in any building. And improper design or improper anchor selection can lead to different levels of what somebody may call a failure. We use failure a little bit loosely here. Typically, however, when somebody assumes a failure, we think of a catastrophic failure leading to a building loss or a loss of life. And certainly anchors are key to collapse preventions. Understandably, it is assumed that seismic anchors are only relevant for the main load path forces such as beams, columns, slabs, and lateral support members. However, we want to point out it is just as important for anchors to support seismic forces that also come from non-structural members. For example, post-installed anchors that support the fire sprinkler systems need to be holed up in a seismic event because damage from the event can cause fires, and the sprinklers need to remain operable after the event to rescue people from the fire dangers. Also, anchors need to support the egress paths of a building, such as stairs, so that people can evacuate properly after the seismic event. And anchors need to keep other non-structural items, such as ceiling tiles and glass, from falling and injuring people, or also blocking egress pathways. So you can see anchoring, whether it's a cast-in anchor or a post-installed anchor, is extremely critical for the behavior in a seismic event. So there are many different types of anchors, and over the years, I think many different types of anchors are starting to be developed. And typically, these anchors are broken down into three different categories that we'll discuss here. So first and foremost, you have cast-in-place anchors. I think many people are familiar with cast-in-place anchors. This includes deformed reinforcement or rebar, and threaded rods. And this is very common for building construction. Used to attach steel fixtures or attaching new concrete to existing concrete or masonry base materials. These are very common in ACI 318, and ACI 318 provides the design information for how to design these anchors in seismic conditions. However, we see a lot of new innovations in cast-in-place anchors as well, with cast-in anchor channels with anchor legs, and this offers ultimate flexibility for attaching facades to concrete structures. And there are also a lot of new innovations with cast-in single-point anchors for mechanical systems primarily, and these offer contractors the most productive systems for hanging MEP systems from slabs. In addition to cast-in-place anchors, there are generally two categories of post-installed anchors. Post-installed mechanical anchors consist of primarily undercut anchors, expansion anchors, and screw anchors. These anchors are primarily used to attach steel fixtures to concrete or masonry base materials. These anchors are typically easy to install, very cost-effective, and offer the contractor an immediate load on the system. These anchors come in a wide range of diameters, typically from 1/4 inch to 1 inch, and usually up to 10 times the diameter in embedment depth, although this can be longer in some situations. These anchors are used for structural systems, but also used for a lot of non-structural systems, such as window attachments, hanging threaded rods for pipes and sprinklers, and facade attachments, and many other applications. And last but not least, chemical or adhesive anchors consist of an adhesive, like a glue, and a steel element, such as a threaded rod or a rebar. The steel element is inserted into the adhesive, and then after a cure time, the rod or rebar can be loaded. While the cure time does not permit immediate loading, the benefit compared to mechanical anchors is that you can install much deeper for higher loading capacity than mechanical anchors, and you can attach rebar to existing base materials, which cannot be done with mechanical anchors. These are the different anchor categories and types, and they will all have varying load capabilities. However, most will have the ability to be used in seismic applications if they have been tested accordingly. So we have the question about the functionality of anchors during a seismic event. The purpose of this anchor in a seismic event is to transmit the seismic forces from the structural or non-structural element into the main building structure, of course. That anchor must be able to resist those dynamic forces coming from the ground motion. And not only must the anchor be able to resist the dynamic forces during the event, but they must be able to support a residual load after the event so that the building can remain serviceable for further evacuation and even to remain in the building after the event. In general, you want to try to drive a ductile failure where steel yield and help where steel is yielding and to help dissipate some of the forces from the seismic event. This is typically done with cast and headed anchors where the embedment is deeper, which can drive a steel failure. ACI 318, which is the governing reference code for concrete design, does a good job of explaining how these anchors can be designed based on their load level and whether or not the designer can drive a ductile failure in the event of an earthquake. In the best case, a ductile steel failure of the anchor or with a plastic hinge in the member is best, as a ductile member will help distribute and dissipate seismic forces. This can be seen in ACI 318 section 17.10.5.3a and b. If it is not possible to drive a ductile failure in the design, or if the steel itself is not made from a ductile material, then you need to either design the anchor for the full capacity of the structural system it is intended to support, or you would add more seismic load to the system as an added safety to prevent the brittle concrete failure. Another way to drive ductile failure is to provide a proper stretch length in a bolt, which is typically about 8 times the anchored embedment depth. Whenever possible, providing the stretch length can be very important for connections where ductility is required. There have been a lot of innovation and technical advancements for anchoring that have been happening in the last 40 years with both cast-in and post-installed anchoring technology. The first wave of innovation was really related to trying to improve the overall load capacity of post-installed anchors. Cast-in-place anchors have been around for many, many, many years, and the first innovations of post-installed anchors, we were just trying to make sure that we could provide something that was easy to install, but still gave a decent load value, even if it didn't come all the way to the level of a cast-in-place anchor. And then the next step happened around 2005. ACI 318 included into their reference code the Appendix D at the time, which considered anchor design in cracked concrete and also include new provisions for seismic anchors. So now manufacturers had to consider cracked concrete in their designs of their anchors, and we needed to make sure that the anchors are a little bit more robust than their predecessors to meet the high demands of the building structures in the new ACI design requirements. Over the years, the anchoring systems become much more robust, and at some point, our post-installed anchors, we were getting really, really close to the capacity of what the concrete limit can achieve. So most of the anchoring systems that are available have been tested to the rigorous ACI 318 standards for seismic. And so we come to a next wave of innovation, which is really related to contractor productivity and developing solutions that can be effectively used for any situation that comes up on a job site. As shown earlier, cast-in technology is advancing very fast. Many contractors are using pre-installed devices rather than post-installed devices, along with computerized BIM technology to maximize productivity and flexibility on the job site. Cast-in anchor channels have been a fantastic innovation for the facade industry, as it offers the strength of a cast-in anchor with the ultimate flexibility of a post-installed anchor. The installation into wet concrete does not have to be very exact, as the slotted holes in the facade fixture and the channel itself slot mean that the facade panels can be lined up exactly even with an imperfect installation. Additionally, single point casting anchors are now allowing mechanical contractors the ability to use BIM systems and to plan out their anchor points for easy installation on top of a concrete form instead of going up on ladders or using scissor lifts and drilling overhead. These integrations with computer-aided modeling will continue to be a path forward in the future. We talked a lot about non-structural systems earlier. We also have developed a drop-in anchor with a sleeve that now allows for easy installation and cost-effective drop-in anchors that are used to hold pipe supports, but can now also be used for structural applications with seismic testing. We're developing hollow drill bits and other anchoring systems for chemical anchors that allow the installer to drill and install without additional cleaning of the drilled holes before the chemicals are installed. And I think even though we are getting close to the limits of what anchoring can hold, there's really no limit on how we can keep developing these anchoring systems for maximum job site productivity and the flexibility, and ultimately what we want is safe buildings. So now that we know that the seismic loads are difficult to predict, how should we design the anchors and structures to improve the overall safety? And this is a great question. We've talked a lot about how important it is to design anchors to carry seismic loads. And we've talked about how you should consider both structural and non-structural applications. And of course, there are many anchors available out there to use. And it may be difficult to determine what is okay or what is not okay for seismic. Fortunately, ACI does a very good job and has established the rules through the ACI 318 reference code. ACI 318, as I mentioned, is the reference code that is used for the structural engineer to design the concrete structures such as beams, floors, columns, slabs, shear walls, etc. ACI 318 Chapter 17 tells the engineer how to do the anchoring design for the attachments to concrete. Now, whether this is a cast-in-place anchor or a post-installed anchor, ACI 318 Chapter 17 is the correct method for doing those anchor designs. And then in addition, Section 17.10 of ACI 318 gives the seismic provisions for that anchor design, again, for both cast-in-place and post-installed anchors. ACI 318 Section 17.1.2 goes even further to show the anchor types that are permitted. For cast-in anchors, these are headed studs and bolts or hook bolts that meet the requirements of 17.12A and B. And then for post-installed anchors, 17.12C, D, and F states that mechanical anchors such as undercuts, expansion anchors, displacement-controlled anchors or drop-ins, and screw anchors, they must be tested and qualified for ACI per ACI 355.2, and 17.12E states that adhesive anchors must be tested and qualified for ACI 355.4. Now this is very, very important. ACI 355.2 and .4 are test criteria that Hilti or any other anchoring manufacturer must follow, and the test includes provisions for the seismic design. But not only does it include the testing provisions for seismic design, but it also requires that those tests are performed at an external lab that is an ISO 17025 accredited test lab, and that the manufacturer maintains a quality control system over the life of the product so that the anchors that are manufactured in 10 years perform in the same way they were tested 10 years previously. This is a very important point to understand. The test must be conducted at a qualified facility, and that there must be an ongoing quality control program, basically audited and reviewed by an accredited third party. But how do you know that your post-installed anchor that you want to use has been tested for ACI 355.2 or 355.4? There are two main bodies that will evaluate test data in manufacturing quality control systems at this time. And then those bodies will produce an evaluation report that shows compliance to 355.2 or 355.4. These conformance and assessment bodies are ICC Evaluation Services and IAPMO Uniform Evaluation Services. Both conformance assessment bodies are ANSI accredited, and they are accredited to ISO 17065. In an evaluation report from either ICC or IAPMO, There's a section which states that the tests have been performed per ACI 355.2 or ACI 355.4, depending on whether it is a mechanical or an adhesive anchoring system. If the evaluation report from ICCES or IATMO UES states that this has been evaluated per ACI 355, then it has been tested in an ISO accredited third-party lab, and it is part of an ongoing quality program overseen by ICC or IATMO. So now we have a product, but another important aspect to seismic design is the proper detailing. We talked previously about the need to have a ductile failure if possible, and we talked a little bit about stretch length. In Chile, unfortunately, there have been a couple of large earthquakes where we have been able to study structures and building elements, and many have undergone significant damage, but some have survived multiple earthquakes. Many towers had anchorages that had great stretch length in tension members and had a steel with a nice ductile behavior. Pictures of anchors here we have shown with a stretch length and necking during event, which had prohibited the failure of the anchors, and the anchors with mild steel were able to resist quakes from 1960 through the earthquake in 2010. And we actually have an example of an anchor that resisted over time, probably multiple earthquakes from 1960 all the way through 2010, and survived the last earthquake and has been since replaced. So detailing of the anchors to include stretch length to include mild steel bolts, and to separate the shear from the tension bolts with shear lugs can significantly increase the likelihood that a structure can survive the event and last beyond the event. Hilti has been running independent studies on anchors for over 40 years. We have 4 test laboratories worldwide that all have seismic equipment, and we're constantly looking at how we can improve all of our anchoring solutions with a high focus on how these anchors perform in seismic situations. Recently, we have undergone a partnership with the University of California in San Diego to study seismic design. This includes a 7-story full-scale building on a shake table using many different types of base isolation and different types of structures, and we see how the seismic performance happens with the building, and not only with the building itself, but the different components where the anchors are attaching different components in different situations to attach both structural and non-structural components. So we've been doing this for about 10 years, and the research will be continued for many more years to come with the University of California in San Diego on this seismic activity. At the moment, the next wave of anchor understanding and innovation is in regard to sustainability. How do cast in and post-installed anchors perform over the lifetime of a structure? What external elements like atmosphere, corrosive elements in concrete, and other things we have not previously considered should we consider, and how we use sustainable and environmentally friendly products and materials in our production methods. In general, we will never stop innovating our products, even if we begin to maximize the load our products can see. So we thank you for listening in on this discussion on anchoring, both cast in place and post-installed anchors in seismic conditions. Obviously, we've gone over a very quick snapshot of the importance of anchoring design for seismic, and we'd love to share more information for you if you have further questions. If you do have further questions, please feel free to reach out to our colleagues here in Hilti, Chile, and they'll be able to help you further on anchoring design, especially in these seismic situations.